Okay, so we've seen a couple of simple forecasting techniques, and now there's one point that I think is very important. Many people don't really understand it, and I think if you understand that and your stakeholders, the people who you communicate your forecasts to and who later will use these forecasts, if they understand that, then you will be so much better off. So the thing is, point forecasts are always like forecasting is always probabilistic. Okay, no matter if you do point forecasts, you do probabilistic forecasts with intervals or whatever it is, forecasting is always probabilistic. What does that mean? So when we forecast a future value, y t plus horizon h, yeah, we are really forecasting a distribution. The probability of this new value given all the information that we have up until now, which is time t. And now a point forecast, yt plus h hat, is really just a single number summary of this distribution, right? And now it is important to understand that this single number summary is not necessarily the most likely future value, but the value that is optimal under your chosen loss function, right? And we get to what that really means in a moment. So point forecast is a statistic of the forecast distribution, and therefore it has statistical properties, it can be biased, it has a variance, and so on. Yeah, so now if we consider this point forecast as an optimal decision, so we can now have this loss function here, L, A, and Y, and this is the loss for predicting A when the outcome is Y. Okay, and now what we do is a point forecast is we want to have the our forecast to be in the minimal A under this loss. Okay, so what that means for us is that if we use different loss function, we get different optimal summaries. So if we use a squared loss, which would be this one, the optimal summary statistic, which is the point forecast, is the mean of the forecast distribution. If we do absolute error, it is the median of the forecast distribution. And if we do 0-1 loss, then it is the mode. So basically only if we, in these three examples, only the 0-1 loss is the point forecast, in this situation, the point forecast is the most likely value. Otherwise it is not. Okay. Well, and now basically, so if we do the L2 loss, right, so then, which is actually the most common thing in practice to do, right? So we do these squares, many time series models do that. Then the forecast is the expected value of the predictive distribution. Absolute loss, the median, as we've just said, that is then robust to outliers. And this 0-1 loss, where the idea is, well, only if we predict exactly the correct value, the loss is 0, otherwise it's 1, then the forecast is the most probable value. And you see this loss, it's not very useful in practice because you will never get absolutely right your forecast. Okay, so let's look a little bit into this idea of the most likely future value, right? So if we say, because commonly people would assume, well, a forecast, that's the most likely future value, like what we think the value is going to be, most likely. But statistically speaking, that's now the mode of the distribution. So basically the distribution's peak. Yeah, which is either the value with the highest probability mass in the discrete case or the highest density in the continuous case. Yeah, and typical point forecasts are not modes. So the most classical forecasting methods like ARIMA, ETS, or just classical regression, they produce mean forecasts, not mode forecasts. And only under symmetric unimodal predictive distributions like Gaussian distributions, there obviously the mean, median, mode, it's all the same. So it doesn't really matter. But in many other distributions, it does matter. So you should always think what loss is implicit here when you evaluate or interpret point forecasts. And just to give you an example of this and how important this is, so let's say we have a forecast distribution for tomorrow's rainfall. We say we have 80% chance that it will not rain at all. We have 15% chance that we will get 5 millimeters of rain, and we have 5% chance that we will get 40 millimeters of rain. The most likely outcome is obviously it's not going to rain. Okay. Also the median, because the median is a 50% quantile, and you see we have here 80% chance no rain. Even the median is a 0. And now the mean, that's the expectation of this thing. So, well, that's the way you calculate the expectation. You take the outcomes multiplied with their probability. So the mean is 3.25 millimeters of rain. Right, so if we now use a model with squared loss, like, as I say, the standard implementations of many of the classical methods like ARIMA, ETS, or if you just use L2 loss in your machine learning method, then you will get a forecast of 3.25, right? And then you report that to your management, and they say, but isn't it going to be 0? So 3.25 is not at all a likely value in an everyday sense, right? But it is the mean of the forecast distribution that we've chosen in a way to minimize the expected squared error, right? So you see here the question is, what error are we going to use later to evaluate our forecast? If we use RMSE, then this value will minimize RMSE, even though it's not at all a realistic value, right? So if you now report this value to management, they say, where does this value come from? I don't believe that. It's not going to rain anyway, right? And then you say, yes, well, if you want the most likely value, which is a mode, that's going to be a 0. And also if you want to look at the median, that's a 0 as well. But if we want to use squared loss, it's going to be something else. So, right, so this is very important, because I think like a lot of times you communicate a forecast to a stakeholder, and your forecast, for example, is just a flat line. Or something like that, and they will say no, but that cannot be true. And then you have to say, well, I'm not telling you this is the future. I'm telling you that this is the forecast that will minimize some expected loss over the future. Okay, and another concept that is also very important and that we're going to use later on as well is the definition of stationarity. So I'm going to take you through this briefly. So there is the concept of strict stationarity, where the idea is that a time series is strictly stationary if basically like for any k and any time points and any shift h, right? So basically you have a window. No, you choose that window however big you want, right? And you shift it wherever you want. And the distribution of the values in that window stays the same, right? So the entire joint distribution is unchanged by time shifts. all moments like mean variance, skewness, they are all time invariant. That's strict stationarity. And then we have this concept of weak covariant stationarity, where we say a series is weakly stationary if it has a constant mean, a constant variance, and the autocovariance depends only on the lag, right? And now you see obviously that if we have a trend, that's not stationary because the mean changes. If we have seasonality, even that's not stationary because the mean changes. So, you know, if you say I have a window in summer, I have another window in winter, and the mean will be different. Yeah, and another example is so a random walk that we have seen earlier, that's also non-stationary. So, well, the random walk here is a formula that I haven't mentioned before. So basically we have the next value, yt is the last value, plus this innovation term, and this innovation is IID noise with a mean of 0 and a variance of sigma squared. So you can now basically kind of roll that back all the way to your very first value, and then you see it's just the sum over all these noises. And what that means is that in the random walk, the variance actually grows with time. Yeah, so that means a random walk is not stationary because the variance is not constant, so it violates even weak stationarity. What that also means is that these shocks accumulate permanently, so there's no mean reversion. So it doesn't kind of go back to the mean. Yeah, and the distribution just spreads out without bound, right? So a random walk is neither strictly nor weakly stationary. And yeah, we're going to talk about stationarity in the REMA modeling, and then we're going to talk about it later with the machine learning models, because it's very important, this question of stationarity, how to deal with it and how to handle it. And here you get the mathematical definition.